Okay, I'm going to go now through some further examples of the momentum equation. So this first example I'm looking at here is the force on a pipe or a hose nozzle. So when the pipe gets narrower at the end, we see the pipe getting narrower, goes out of the end and into the atmosphere, into the air. So within the pipe, it's at a certain pressure, we'll call that P1. P1 here, and it comes out into the atmosphere, and the pressure will be at this point atmospheric. And it's going to go from a diameter at 1 to a narrower diameter at 2. So the velocity is going to increase because it's by continuity. We reduce the area, so the velocity must increase. So if we're told here the velocity out be u2 is 10 meters per second. Remember that's very fast. Inlet diameter, so diameter at 1 is 50 millimeters. Outlet diameter is 30 millimeters. Find the pressure force. So find the pressure P1 and the force. Well, to calculate the force, we would have to calculate P1. So we'll just go through that process. Let's just calculate the areas. Okay, these are very small areas, so I've written them with 3 significant figures. Let's work out what flow rate we have. It's just area times velocity. Now we know velocity u2, so we use u2. She's got an easy calculation. 0.707 times, so 7.07 times 10 to the minus 3 meters cubed per second. Tiny again. 3 significant figures. Velocity u1, says v1 there, let's keep it as u1, is then 3.6 meters per second, and we get that by dividing the 0.00707 by the area A1. Pressure P1 we get from applying Bernoulli from point 1 to point 2 to here. We're trying to find this unknown P1. We know U1, we know U2. P2 is atmospheric, so we can cancel that. Z1 and Z2 are equal, so we can cancel that. It's horizontal. Pressure P2 is atmospheric. Now if we were measuring gauge pressure, we could ignore the term and effectively take gauge pressure as being P2 as being 0. But let's take let's in this occasion take atmospheric pressure as 100 kilonewtons per meter squared. So we're going to calculate pressure 1 as being an absolute pressure. And all it is a bit of a rearrangement of that Bernoulli equation to give a pressure P1 of 143,520 newtons per meter squared, or 143.5 kilonewtons per meter squared. Right, we now need to work out the force. Now, the force due to the pressure is P1A1 minus P2A2. Simple calculation. Comes out to be 210 newtons. The total force is rho q u2 minus u1 in general, and in the x direction. So we're only working in the x direction, so it's u2 minus u1 times rho q. That comes out to be, if we put the numbers in there, 45 newtons. So fairly small forces compared to what we've been working with elsewhere. Resultant force is total force minus the pressure force. We have no body force, so I've neglected to write that down, so we would be subtracting body force. But as it's in the horizontal, we don't have gravity affecting this flow. So the resultant force is a minus 165 newtons. Minus, because it's going in the direction opposite to the direction of flow. So that's the force on the nozzle. Is the opposite of that, which is 165 newtons. So if you've got a firefighter holding this nozzle, they've got to be able to withstand a force of 165 newtons. So about 16 kilograms, equivalent to holding a weight up, which 16 kilograms not very heavy, but holding it for a long time is a lot of force required by a firefighter. So let's have a look now at the force of a jet hitting a plane. Now, what's the arrangement here? We've got a velocity jet of fluid, it's open to the air, travelling towards a plane, a flat plane at right angles in this case. In the x direction, and y direction is vertically up and down, up, positive up, down negative. And we're saying that the jet splits equally, going up and going down. So control volume, shown by the the dash box, we have a flow going in and we have two flows going out. The question is, what is the reaction force of the plate? What force does the plate need to withstand to not move? Same analysis as a pipe using the momentum equation, step 1, as we do with with all these force equations. Draw a control volume. We've got our coordinate system, which I've mentioned, x in the horizontal direction of the fluid going in, y in the vertical of the fluid going out. The total force, rho q u2 minus u1 in the x direction, because there is no velocity in the x direction, it's minus rho q u1. Symmetrical, so the total force in the y direction is balanced by the fluid going up and down at the same time. Pressure force is the pressure at the inlet and outlets taking atmospheric as 0, then the pressure force are going to be 0. The body force, well, let's say this is quite a small volume of fluid, so we're going to take the body force due to gravity, the weight of that fluid in a small volume as negligible, effectively almost equal to 0. Fbx will always be 0 if it's at right angles to the gravitational direction. So the resultant force is Ft minus Ft, the total force, equal to resultant force minus the pressure force minus the body plus the body force. So the resultant force, we're just rearranging that. In this case, it's just the equal to the total force, which is minus rho q u1. That's the force that the plate has to, or the plane has to withstand. So the force on the plane is rho q u1. Let's have a look at an inclined plane. Very similar, but slightly different analysis. If we noticed, I've got the axis system line, so the y direction is along the length of the plane. This makes it slightly easier. Alright, now it is stressed a little bit. This will simplify your analysis so that we'll be able to ignore the force in the y direction. Force on a curved plane, similar to a pipe, but you've got atmospheric pressure all over and you've got pressure, so the volume going in is equal to the volume going out, so the areas are the same. Pressure always atmospheric, atmospheric, cross section is the same, and the velocity thus stays the same. Control volume, same as we would draw for a pipe. Total force in the x direction, rho q u2 cos theta minus u1, u2 equals u1. So we can simplify that total force equation, getting rid of the u, replacing it with the q. So we have a q squared over a cos theta minus 1. And in the y direction, similarly, we get we can remove the u and replace it with a q. So we've got an unknown q. Pressure force, well, the pressure and area are the same at the inlet and outlet, so the pressure force are 0. Body force, x down, equal to the weight of fluid. Again, we're going to ignore the weight of the fluid. Or, if it's a significant volume, we can include the weight of fluids, and it's rho, it'll be minus because it's down, and the vertical axis is positive, going up. Minus rho g times capital V there represents volume of the fluid. So we can almost neglect it. Resultant force then is write total force equals resultant force plus pressure force plus body force, and we'll the pressure force and body force are 0 in the x direction, so we get the resultant force in the x direction to be that. In the y equation, if we're going to include body force, we have that, we don't cancel that, we calculate this force in the y direction. As usual, we do Pythagoras and trigonometry to find out the resultant forces. So that was an example without any numbers. Remember what the momentum equation is. It's simply a statement of Newton's second law. Total force on a fluid is equal to the rate of change of momentum through a control volume. And this force acts on the fluid in the direction of flow. So as a nozzle, this is negative to push the fluid in. A momentum equation gives total force, which has 3 components: resultant force, body force and pressure force. The resultant force is the external force, the thing that's the fluid is acting against. In a nozzle, it's the thing that's squeezing it narrower. In a bend, it's the thing that's causing it to turn around the bend, the pipe. The body force is the weight and always acts down. And the pressure force is a difference due to the difference in pressures and areas. As a summary of the equations, if we write our coordinate system in x horizontal, y vertically upwards, and the angles are measured as shown here. And the slide just to summarise Pythagoras and trigonometry to calculate the resultant force and the magnitude and direction. Let's have a look at some examples with some numbers in here. So a vein or a curved shape open to the atmosphere. It's 75 millimeters wide, that's into the screen, 25 millimeters deep, that's thickness, so we can work out the area from that, be a rectangle, and the velocity is going in at 25 meters per second. It's very fast, that. It's not in a pipe, so it does occur. It occurs in things like turbines, open to the atmosphere, remember. We've got atmospheric pressure here, atmospheric pressure here. So it's going in at 45 degrees and coming out at 25 degrees. Area, small number. I've used 4 significant figures here. Q, I've probably should have used 3 significant figures, 4 significant figures to be consistent. Area in is equal to the area out, so we've got an area. Velocity in is equal to velocity out, so we've got a velocity at the end and outlets. Let's simply calculate the total forces from putting in our numbers in the equations. We get 33 newtons in the x direction, 1,324 newtons in the y direction. So this is turning it and forcing it in that direction. Pressure force, they're equal and 0 because the pressure is atmospheric, the areas are equal. Neglect weight, small volume of fluid, so we're going to neglect it in this case. No body force. Resultant force then in the x direction is minus 233 newtons, and in the y direction minus 1,325 newtons. I've drawn a force diagram so that it is in those directions of negative x, negative y, and we see that F due to the fluid is causing on this shape, on this blade. We get an angle of 80 degrees, 10 to the minus 1 of Fy over Fx. So is the example now of the jet hitting an inclined plate, 75 millimeter diameter jet, velocity 25, again very fast, plate angle 30 degrees. Choose our axis system. So the y-axis, the x-axis is parallel to the y-axis. We could turn it round and make it look like that if that's helpful. Calculate the area, again small, got it to 3 significant figures. Flow is quite small in this case, 11 litres. 110 litres per second, sorry, 0.11 meters cubed per second. Total force, equation, we calculate that. There's no U2, no U2 in the x direction, yeah, so because it's all vertical, FTY comes to be, FTX comes to be 2,381, FTY, similar calculations, FTY is 1,375. Pythagoras gives us a resultant force of 2,750 and the angle of 30 degrees. So just want to mention the lab, which I've mentioned previously in lectures. We're going to be doing an experiment of looking at the force due to a jet being fired up the centre of this vessel onto a balance plate here, which will have weights on, and because we can calculate the force due to the weights, due to the masses, we can balance that with the force due to the jet. So that's the jet's rig, as we'll call it. Some equipment, stopwatches. You might want to use your phone as a stopwatch nowadays, and some weights and some different shaped targets, from a flat target to a hemispherical target, which returns the flow back to where it came. This is a diagram, and this is an arrangement for a diagrammatic arrangement for doing some analysis. Now you'll see details of this when you get to do the lab in May. Okay, thank you very much. We've summarised the momentum equation again through example. We've looked at forces on a curved vane, We looked previously at force on a bend, and we've looked at examples of force of all of these and forces due to a jet hitting a target.